Hello, my name is Pierson Guthrey, and I would love a chance to tell you why I belong at Courant. Let me start by showing you something that I find incredibly interesting.
The method of lines is a theorem that takes a PDE and combines concepts from numerical methods, such as approximating the second derivative, and linear algebra, such as handling the system of differential equations. We can turn that into something easier to solve by representing it as a matrix and performing an eigenvalue decomposition. This allows us to make a substitution and end up with a system of ODEs that is much easier to solve. Then we can go right back to our original variables. This theory is something I show my friends to demonstrate the kinds of things you could do in computational mathematics.
My academic background is in Tulane University's Engineering Physics department. They do a lot of quantum mechanics and materials science, so as you can see, one would naturally run into a lot of ordinary differential equations and partial differential equations. That's why I started getting interested into applied mathematics. I started also taking some math courses that I found informed my physics classes, whereas my physics classes didn't necessarily inform my mathematics classes. It was a non-reversible process. One course I took, computational physics, was sort of this mathematical physics hybrid class where we did some introductory computation and numerical methods. That class really fascinated me. I actually applied to the Center for Computational Science right after that semester, and they accepted me into their Master's 4+1 program. My focus was on PDEs that could be applied towards physics or material science that I could use in my physics classes that I was still taking my senior year. I wanted to have this strong mathematical background in applied mathematics so that I could breeze through physics problems. One of the professors at the Center for Computational Science, Dr. James Hyman, actually was the one who told me about the Courant Institute. I decided that would be a really good choice for further graduate studies, and so I decided to apply. And looking at the website, I saw that it was very interdisciplinary, and they mixed with a lot of physicists and mathematicians, also biologists and chemists. So when you have all of this interdisciplinary work going on, it's really easy to find yourself a place where you can get the applied mathematics background you need, but still very readily apply it to problems that you're interested in. At the Courant Institute, there's a broad spectrum of topics that you can apply your applied mathematics background to. At the Center for Computational Science, we looked a lot at fluid dynamics, but we didn't really touch on nonlinearities as much as I really would have wanted. They're really important, and they are often unavoidable in real-world problems. My thesis did touch on them a little bit. We had a pressure wave moving through a material, heating it. And we found if we just ignored the nonlinear term, you had maximal heating at the boundary. But as soon as you include the nonlinear term, maximal heating would actually happen at some distance into the material. That's a huge change in how the solution to the problem behaves. Linear is nice, but nonlinear is where it gets really interesting. How do we deal with nonlinearities? This is a big question that I want to pursue, but I would need to go pursue graduate study in order to do so. I hope you agree that the Courant Institute is a good match for me, so that I might pursue my academic goals and pursue further research. Thank you very much for listening, and you have a good day.